Hi, my name is Soumyadeep, and today we'll be talking about the table sample clause, which is a new feature for Greenplum 7. So the key idea behind table sample is you want a sample of your table, right? You don't want to scan the entire table. You want a sample of your table, and you want this primarily to gain a speed up. That's the primary use case. Now, this isn't new. This has been around in the SQL community. It's been part of the SQL standard since 2003. It was introduced in 9.5 Postgres, and what we did for Greenplum 7, which is based off of Postgres 12, is to make it work in an MPP environment, and of course, modify it such that append optimized tables are supported. So what it boils down to is very simply, for each and every table in your query, in the from clause, you can affix a table sample clause. And optionally, you can specify a repeatable argument with which you can control which random rows you see. So for example, what that means is if you want to select 10% of the rows of a table, line item, let's say, you can just say select star from line item table sample system 10, and it'll give you 10% of the rows of the table. Now, if you want the same results across queries, because this would return you a random result every time, you can just specify repeatable and then a seed, which is any number. So what kind of applications would table sample have? Well, you would typically think about high frequency sensor data or high frequency stock market data or very high frequency data that is ingested. And there's a high level of redundancy. The data the two nearby points don't differ that much, right? So in that case, it's possible to obtain a fair sample of the table for speed and still not sacrifice accuracy too much. Like that's what happens, for example, this is from a DB2 paper. Somebody ran linear regression with no sampling versus 0.01% sampling, right? And you can see there's not much of an error between running linear regression on the full table and on the 0.01% sample. So this kind of gives you an idea of the kind of applications you might want to even have an aggregate, like average of a specific quantity, and you can just take a sample, and that might do the trick, right? Or you want to randomly reduce, or you want to reduce the size of, let's say you want to shrink your table 50%, and you want to do that in a fair way, right? So that you delete rows uniformly. You can do that with the table sample clause. Just put it in the delete statement in the from clause, again, next to the table. So there is the table sample clause, but there's also other ways to get a random set of results, right? So we can talk about query level sampling. So the results of the entire query, what you can do is you can take the entire query as is, then you can attach a random clause like this. This just means give me 10% of all the rows of the query, right? Whatever query you have in here. So why not just use this, right? It is definitely more powerful because you don't have to go and write table sample next to each and every table in your query. And it seems to have better semantics, a more powerful semantics. This might what you want. You do not have to go and write table sample everywhere. However, it does not give you the performance that table sample would give you. So that is very important, and we'll see that very soon. So what do the sampling methods look like? So all of them implement the TSM API, which is a way to you can write your own table sampling method. Some of them are already provided, but they fall into two major categories. One is block sampling, the other is row sampling. So what block sampling basically means is you select the blocks. You select, let's say your table has 100 blocks and 10,000 rows, 100 rows in each block and so on, whatever, right? When you select a block, you select it probabilistically. And once you select the block, all the tuples in that selected block are going to be selected in the sample, right? And this is the most efficient way to do sampling. But there's also another way, which is row sampling, where each and every tuple is examined and you run the probabilistic experiment on each and every tuple. And This is, of course, more performance intensive because each and every tuple has to be considered. However, you get a better sample in terms of quality. That is, there are no clustering effects. But again, if you have a large enough table, you don't have to worry that much about clustering effects. And with the repeatable argument, you can always iterate to find a good sample. So let's just see this in action really quick, right? So I have this line item table. It's around 28 gigabytes in size. And it's a compressed append optimized row, AO row table. And what I'll do is I'll just select a random sample from it. You can see this gives you a random sample. I use the Bernoulli method. And you will notice that we get different rows in the results. So you get the seated column that gives you an idea of this is the tuple identifier. You get completely different results. You get a completely random sample. Now, if you want the same sample over and over again, just specify repeatable 0 or repeatable whatever you want, anything. And you're going to get the same results each time. So using the same seed, we should expect to see the same results. There you go, same kind of results. You can identify that easily with the seated column. Now, there are other ways also. You can do system. See that the sample percentage is very, very low for this table, 0.005%. So in one run, I might not get something. If I change the seed around, I might get something else, right? So that's system. Now this other ones that I mentioned, system time and system rows, right? So both of them are extensions. So you have to create, so it's called TSM system time. Let's do that one first. So let's say I want to sample the table for, let's say 500 milliseconds, and whatever is returned is returned. There you go, random results. If I run this again, you'll see different set of results, right? So that's around roughly 500 millisecond sampling. Similarly, we have TSM system rows, and you can specify, hey, I want 10 random rows from the table. There you go. That's kind of the demo. So, yeah, we talked about these things. So the sampling process, right? For heap tables, let's talk about heap tables first in terms of the sampling process before we get to the append optimized tables and what we did for that. So for heap tables, the sampling process boils down to this. First of all, you need to select if you don't have a current block, you need to select the next one, right? And if you're doing row sampling, this will always be the next block in the table. So block 1, block 2, block 3, block 4, we'll linearly consider each and every block in the table. But for block sampling, where we actually probabilistically choose the block, we will probabilistically choose the block, right? So it'll be block 1, then you choose block 5, block 10, whatever. So from lower block numbers to higher block numbers. And what you do is, whatever it is, whatever type of sampling it is, you just load the chosen block into shared buffers. So you do not load other blocks, just the chosen ones, right? Once you do that, you can then, inside the block, you can go and pick off offsets. You can say, hey, I want first offset, second offset, 10th offset. That's what row sampling would do. Because row sampling, each and every tuple you will consider and say, okay, do I want to pick this offset? Yes or no, right? And for block sampling, that's not the case. Once you load the block, every tuple in the block will always be considered. So we return all of the tuples. That's just how the framework is. So, and finally, you return that tuple up into the executor, whatever executor node is above the sample node. and it'll consume that tuple, right? And then you keep doing this until you run out of blocks or time, as we saw, or rows, right? Whatever table sample method you use. So what are the challenges for AOCO tables? We kind of have to, fortunately for us, Postgres exposes the table access method APIs, and there are some table access method APIs that we have to implement for AO and CO tables. And to shoehorn AOCO tables into that API, there are certain things that we have to do. So first of all, this API expects fixed size blocks, right? For heap, it's 32K blocks, right? AOCO tables, unfortunately, do not have fixed size blocks. They have variable size blocks called var blocks, which vary by the type of stuff inside the data types and also the compression settings. So, but we need fixed size blocks for this framework. So what we did was we imagined arbitrarily sized logical blocks of tuples, right? And each logical block, we arbitrarily chose 32K number of tuples to be one block. So fortunately, the API doesn't care if it's actually like it's a physical block or a logical block. It doesn't care about that. So we are using logical blocks. Now, these logical blocks can span physical seg file boundaries or whatnot. That doesn't matter. So we have a way to abstract that out. So the next challenge then is, okay, fine, we have a block, right? We have this logical block. First 32K tuples is the first block, next 32K tuples is the next block, and so on. But how do we randomly load such a block? For block sampling and for row sampling, we need to load these blocks, right? For block sampling, we want to randomly load them. So if you had an index on the AO or CO table, you have what is called the block directory already created for them. That's an auxiliary data structure that supplements the AO table, kind of like a toast table for a heap table. So this block directory, if it exists, if you ever created an index on the table, it would help you locate the nth block starting row. This is actually the same interface used for index fetches, which I'll talk about in a second. But with this, it's very easy to look up the file offset where we need to go into the append optimized relation file to figure out to pick and scan that particular tuple out, the starting row of the nth block. And then we can, like, if it's block sampling, we can scan each successive row from there on, right? That's what happens with block directory. But what if there's no index? What do we do then? Then, unfortunately, we'll have to go through, since there's no dictionary or anything like that for append optimized tables, what we have to do is we have to scan the var blocks in sequence from the beginning to the end of the relation across all segment files, right? Because but there is one silver lining there. You can only get away with reading the block headers. So you don't have to read the content. You don't have to decompress the content. You don't have to, you can just skip it. And you do that until you reach, let's say, the nth block's first row. You just keep a count and until you reach there. So that's the second challenge. And the third challenge is once you have this block, how do you randomly access an offset within that block? Now, in heap tables, it's very easy to say, okay, block 5, give me 10th row from the 10th row from that block, because it's just as easy as indexing into the item pointer array, right? No such thing for append optimized tables. You'd have to go through all the tuples before you get there. So, but again, all of this is abstracted out. And fortunately for us, we implemented a way to sample in terms of row numbers, which was used in the fast analyze implementation in Greenplum 7, which is a new method to do very fast analyze for append optimized tables. Right, so we kind of reuse the same infrastructure, and I'll show you how. There's a link to the numbers in the table. So if you imagine your table as a logical sequence of row numbers, it would look something like this, right? And what would happen is, let's say you want to look up target row number 41. Now, the 41st row number may be the first row number in the second seg file. It could be, in this case, it is. Because you can see these are the row counts of each var block in segment number 1, which is 10, 10, and 20. 41st row maps to entry 0 for this block directory entry. So like this, you can figure out, okay, what is the file offset at which I need to go to, and I need to go and return that tuple. So this is what block directory assisted lookup looks like, right? For a specific app, like row number in the space of all row numbers in the table. And by the way, this also includes deleted rows, right? So you have to do a visibility check, of course. So this is with the block directory, but if you do not have the block directory, let's say you're on row 6000 and that's the starting row number of whatever block, right? And how do you do this, right? So what you do is, let's say this is in var block 6, right? Row number 6000. So for each var block, you have to read each var block along the way, and you don't touch the contents of the var block. You just read the header, and whatever's the row numbers or whatnot that's in there, you just skip to the next block until you get your desired row number. You keep a count, and until you know that var block 6 actually has row number 6000, you keep like reading var blocks and skipping the content and moving on to the next. That's what you do, and that's kind of how you do not decompress the content. That's a very important piece of information here. That gives you some savings. So it's not as bad as like scanning the entire table and processing each row in the table. That's not what we're doing here. Although we are reading the entire table, we are not actually processing everything we are reading. So let's talk about the performance experiments that we did. And it's going to be a very simple select query. We're going to do heap and row tables. We're going to do two sampling percentages, 5% and 0.05. And this scale 100 uncompressed size of the table is around 87 gigabytes. Compressed size is around 28 gigabytes. And we're going to do compressed and uncompressed tables, and with and without index, to demonstrate the difference between block directory assisted and var block skipping techniques. And we're going to contrast Bernoulli and system sampling. And we're going to do a mirrorless demo cluster on local workstation. So what that means is that don't worry about the absolute values, just focus on the relative differences in runtime. So let's talk about the baseline, which is basically just select count start from line item. This is a sequential scan on line item. It takes around 56 seconds to do that. Now contrast that with the Bernoulli row level or row-based sampling. You'll see that the sequential scan is now replaced with the sampled scan operator, and it's around the same, around 57 seconds. And that is exactly what you expect, because Bernoulli reads the entire table and considers each and every tuple probabilistically. So it's going to be just as bad as almost as bad as a full table scan. Now, in terms of performance for the scan, if you do look at system, you see the dramatic difference just because of the fact that we are not processing that many tuples and saving so much on I/O, right? So these are all expected. Now let's come to AO-row. I'm going to show you this diagram instead of each and every explain analyze, because there are a lot of experiment parameters here. So first we talk about 5% sample size on AO-row. So this is the full table scan, which takes around 130 odd seconds. Now we had talked about random a few slides back, right? Why don't we use random instead of Tablesample? And this is the reason why, because random is just as bad as a full table scan, because each and every tuple from the scan is going to be returned, and then we will exclude it or include it based on the random value. Plus, it's a function call, and it's not going to be as performant, right? Then we go on and look at Tablesample with system, but without a block directory. And we see an immediate difference between these two, right? We see that we have a performance bump right here. However, we do see that system and Bernoulli are not that different, right? You would expect from the, if you come from heap land, you would expect system and Bernoulli to be poles apart, right, in terms of performance. But without compression and without a block directory, it's not that case right here. There's not much difference, and that's because we are reading the entire table, and we're kind of doing the same thing for system and Bernoulli, right? We're doing var block skipping. Now, immediately, if you have a block directory and you do system, that kind of like 11 seconds. That's exactly like heap, and you get the speed up, right? And then you can go over and look at the compressed case. This is Z standard with compressed level 9. And you can see, again, there's a difference between without the block directory and with block directory for system sampling. Now, if you compare in this case, if you compare the system without block directory to the Bernoulli without block directory, you'll see that system without block directory is winning over Bernoulli without block directory. And the reason is that we are saving on decompression cost. Bernoulli is very bad in terms of the fact that the access pattern isn't great, because we are like randomly reaching out into blocks. We are doing many random lookups inside the AO table. And that is causing a lot of low cost decompression, a low return decompressions, because you're probably just saying, okay, give me a random tuple in a random block. Let's say you choose block 5 and you only want like 3 rows out of it, but you went ahead and decompressed this into this huge block, right? So wasted decompression effort is going to be pretty high with Bernoulli. And you kind of don't want that. Now, let's look at 0.05% sample size, right? And for 0.05% sample size, you kind of get the similar pattern with Tablesample, obviously. But if you look at things like the difference between with block directory and without block directory, if you compare system without block dir with system with block dir, look at the magnitude difference. Look at the speed up here, massive speed up. And that's just because it's just very similar to index performance, right? Because with block directory is kind of like you having an index, you're using the block directory, right? So if you have in general, if you have a query where the index where you're returning a lot of rows from the index versus only a few rows from the index, only a few rows from the index would win. And that's exactly the kind of behavior that you see here. Also, Bernoulli block dir. Yeah. So, and there are some other things that are kind of like summarized over here, kind of what I already talked about. So take a look. And then we can shortly chat about sample quality, right? So Bernoulli, if you use Bernoulli, you get better sample quality, which is what we already mentioned. You can see that the kind of blocks that are returned from this query, like from line item table sample, Bernoulli your system 5, with Bernoulli, you get a much more uniform distribution of block numbers from which you get the rows, whereas a lot less number of rows obviously are picked for system, and also block numbers are not as uniform. This is just a construct that you can use kind of to look at what kind of blocks are being selected in your from your table with the Tablesample. So let's talk about best practices. You want to prefer system sampling or block sampling if the table is large enough. That would give you the best speed up. If you have a block directory, it will definitely offer you significant speed up for AOCO tables, as we've seen, especially if the sample size is much less than the table size, and lesser it is, the better. The Bernoulli would also benefit from a lower sample size. It is possible to evaluate sample quality by looking at the block distribution, which we saw. And what you can do is you can play around with the repeatable option until you get a favorable spread, right? Once you lock in that repeatable seed argument, you can just keep iterating until you find a good or fair sample, fair in whatever terms you have as your expectation. And then Bernoulli is very useful if the table is very small, because if the table is too small, like let's say smaller than one block, then system might return too many rows. So even if you say 5% of the table, it might return a much larger portion of the table if there are not too many rows in the table. In that case, you would use Bernoulli. That's better. So some ideas for the future. According to the SQL standard, the table sample clause you should be able to apply it to any from list item. However, there is a limitation of Postgres because it only applies to regular tables and materialized views. It does not apply to, for example, foreign tables, right? Currently, Orca does not have support for sample scans. So if you run a query with table sample, it will fall back to Planner. This will be added in the future. And then there are interesting integrations possible with our machine learning libraries. It is pretty appealing, if you think about it, to train on n% of rows, n rows, or say you want to train only for n milliseconds. That's a compelling construct that you can use, right? You can actually create a view on the table sample of a training set and just feed that into the training function, and it will train on that, right? And then also you can use a sample for validation or prediction with your model. So many applications are possible. And that brings us to the end of our presentation. Thank you very much.